Oh, we're live! Heck yeah! We did it, guys! We did it. We did it. We did it, people. And I'm seeing the oh, I don't want to do product placement. I'm not getting paid to do this. You can't even see it. Yeah, I'm gonna do some productivity stuff. Mostly maths. Or math. Whichever one. I generally say math, but you can say maths if you're from the UK. Well, it's weird seeing me delayed. We can like have the 20-second sync up because I just drank Coke at the same time I did, but it was like 20 seconds ago. See, there's the second time. Man, I started this bottle of Coke and trying to set up, and now I'm almost done. Product placement! I should not reveal I'm terrible at this. I'm obviously not getting paid to talk about this, even though I'm suddenly now talking about this just because I've been drinking so much the past 2 weeks. That's the only thing we have on campus. Enough of that. Get out of here. I'm like Rick from Rick and Morty, who's constantly burping all the time. It's fine. Okay, so that's cool. We have one person watching now, or is that just me? I honestly don't care. Let's do work together. We're here to do work. So here's my book. Basically, I have final exams on Wednesday and Thursday, so I've got like today, Sunday, Tuesday, Monday, and Tuesday. Basically, like 3 days in a bit. But I'm doing this to motivate myself because I really need to get this done. Oh well. Alright, let's figure out what sections I have to do. I always forget the section numbering. Let's see, URI Math Department. URI Math Department. Math Department. People. Don't ask why the course website is here. It just is. It's kind of strange. It's my professor's. No, not mine. Website. Let's get all the sections. I've done a lot of these problems before, so I'll just have to do the other problems within those sections that I haven't done yet. So it's basically from chapter 12, we've got 12.1 through 12.5. Chapter 13, we've got 13.1 through 13. This probably makes no sense, but, you know, we're here to do work, so we're getting work done. Or you're watching me doing work, that's fine too. I don't understand why you would do that. From chapter 14, I'm doing 14.1 through 14.7. Chapter 15 is just 15.1. Chapter 16, I don't know if we're going to get this far. 16.1 through 16.5. And chapter 17 is 17.1 through 17.3. So that's the sections I'm covering. This is all multivariable calculus, which is what I'm doing this for my math course this semester. So that's fun. Listen to me, Morty. All you've got to do is your math, Morty. Rise above. Focus on science. That's my best impression. It's probably terrible, but you know what? Who cares? I don't. Gandalf says, I don't care about that impression because I can always do this impression and somehow it impresses people. Like when I take the line, for example, and I smote my enemy in his ruin upon the mountainside. Right. I actually need to focus. I need to stop doing impressions. Let's see. The partial derivative. We did that. I mean, we did all of these. Oh, I don't have chapter 12 with me. It's in the book. I'm a dangus. I need to grab the actual book. Not just because loose leaf textbooks, you can actually take pages out. So that's the pages I've been working with for like the second half of the semester. Chapter 12. Oh, it's actually, this is just like basic crap. Okay, that's fine. I don't care. I've probably forgotten this because this is the stuff we did at the beginning of the semester, which is why we're here and this is why we're doing this. Talking about 3-space, the distance formula in 3-space, which is basically derived from the Pythagorean theorem, which is all fun and good. We'll start with the problems. We'll do odd problems only, that way I can check the answers. Problems 27 through 28 use table 12.2 to make tables with the given properties. 27. The temperature adjusted for wind chill as a function of wind speed for temperatures of 20 degrees F and 0 degrees F. What? What does it want me to do? Okay, so here on the table, it has wind speed on the left and temperature on the right. Right, and it's a multivariable function of 2 variables. So you could think of your orthogonal axis. You have wind speed coming this way, and then you have temperature going this way. And what is it measuring? What is the function of temperature and wind chill? Oh, wind chill. So wind speed going this way, temperature going this way. So your wind chill is going to be this direction here, right? It probably looks weird on camera. It's my index finger. Don't worry. I just have a long index finger. Oh my god. Okay, to make tables. Okay. Oh, so once it adjusted for temperatures of 20 degrees and 0 degrees. Oh, so it just wants sections of that table? Is that what it wants? Okay, that's fine. So for 20 degrees Fahrenheit, your wind chill based off of temperature. So for 20 degrees Fahrenheit, what we're basically doing was we're taking. So imagine if you have like a random function, and you have x coming this way, y going this way, and z going this way. What we're basically doing is say you have temperature, wind speed, and wind chill. You're basically taking a slice of the temperature at 20 degrees F here and saying on this slice, based off of the wind temperature here on this slice, what is my wind speed? So you basically transform this 3-dimensional surface into a 2-dimensional function. I don't know how well this is going to turn out on camera. It looks pretty good. So that's besides the point. So basically on this slice, what is the function of wind chill with respect to wind speed at a temperature of 20 degrees and for a temperature of 0 degrees Fahrenheit. So for 20 degrees F, our wind speed we're going to take is wind speed measured in miles per hour. We've got 5, 10, 15, 20, 25, and 25. And so for 20 degrees F on that slice that we just talked about, our wind chill is going to be 13 degrees Fahrenheit. At 10 miles per hour, it's going to be 9 degrees Fahrenheit. At 15 miles per hour, it's going to be 6 degrees Fahrenheit. At 20 miles per hour, it's going to be 4 degrees Fahrenheit. And at 25 miles per hour, it's going to be 3 degrees Fahrenheit. And I'm all taking this from a table. This is not any calculations or anything. This is just a table that represents some sort of surface, and we could graph it out if I had like the tools and stuff. But you know, I could probably do it on GeoGebra. We might do this later if they actually give me a 3D function and we can explore it, because that might be cool. Because I like doing math education. That's one of my things that I like. You know, me as like a gamer, which is like a thing that I like to do, but I also like math education as well. I tutor math because math is fun. Listen to James from The Odd Ones Out. He's right. Math is fun, and you should all like it. Because you don't have to do essays in math at all. It's one of my favorite subjects. Which is why one of my majors is mathematics. The DOI. I think there's a police car. Alright, for the 0 degree slice, at 5 miles per hour, we're at negative 11 degrees Fahrenheit. At 10 miles per hour, we're at negative 16 degrees Fahrenheit. At 15 miles per hour, at negative 19 degrees Fahrenheit. At 20 miles per hour, at negative 22 degrees Fahrenheit. And at 25 miles per hour, at negative 24 degrees Fahrenheit. So that's what the question is asked. It just wanted us to take those two slices of the surface and find those values. Okay, let's go to the next question. Question 29, because we're skipping the even ones, because that's what I do. Give tables for beef consumption as a function of p, with I fixed at I equals 20 and I equals 100. Give tables for beef consumption as a function of I, with p fixed at p equals 3.0 and p equals 4.0. So it wants 4 tables this time, based off of, again, they gave us another table here. So this is like the same thing. Again, we could do a million of these, but I'm not going to do problems that repeat themselves. If I already know how to do one of them, I can do all of them. For problems, so we'll skip to problem 33, that's fine. By the way, I'm at that point in math where your professor doesn't check your math homework at all. Like, the only reason you do the work is because if you don't, you're probably going to fail the exam. It's just, math is not something that you can just get immediately. Like, you can get it conceptually, but unless you spend the rigor in actually practicing the problems, you're not going to do well at it, because evidence shows and research has shown that experiential learning is the most pertinent of the ways you can learn something. And this is especially true with respect to problem and application-based courses. So courses like chemistry, courses like mathematics, stuff like that. So this is super important to do practice problems. So do practice problems, practice. Right, this is very important. I like how one person tabbed off me, and no one's watching now because I'm talking about math. And math is boring. But to me, math is fun. So it's about math. Math is fun. At least 2 people watched, so I don't care. It's gonna be on here on YouTube forever. Damn you. Okay, a person's body mass is a function of their weight and height, given by BWH is they give us an actual function. Okay, so their body mass, BMI, is a function of mass and weight. So here they're saying it's W over H squared, and basically B as a function of W and H is going to be equal to that. So this is actually going to be an actual function that I can show you. So let's actually do that. So I'm actually going to load up GeoGebra, and we can actually show you what this looks like. So, programs. Actually, it would be under apps, wouldn't it? GeoGebra Classic. So I'm going to go to 3D calculator, and in a minute I'm going to switch to the 3D graphics. It's super important. Okay, and then I'm going to switch so you can see what I'm looking at. So window capture, properties. This is going to be not Firefox but GeoGebra. We're not going to capture a cursor. Okay. I'm going to take it and put it like here. I don't want to like get my face. Or oh yeah, we can move this over here, and then enlargen this. I can move away from the camera like that, so we can give it more room, just like that. Awesome, awesome sauce. Let's see if it. Why is this not working? Window capture, properties. Weird. It doesn't like it. I guess we'll remove this layer. Remove. Yes, I feel like this is wasting time, but I really want to show what a 3D function looks like. Oh, I didn't mean to do that. That's bad. Now it's all black. It's all black! A video capture device. Okay. I'm back. Finger video. Okay. Okay, it's the same settings as before. We're back. How did I get rid of myself? That was weird. Okay, plus. Window capture. Okay. Okay. It doesn't want to be captured. That's weird. Okay. So that's not gonna work. Properties. I could show maybe Mozilla. Okay. Well, that's odd. Okay. And I'm gonna do that. And I'm gonna do that. Okay, we'll put that there. I'm just like messing about. Okay. That's as good as it's gonna get. Okay. Now I can close GeoGebra, because that's not gonna work. We can probably find it online. GeoGebra 3D graphing. Yes. Yes. Excellent. Excellent. Ooh. Man, I really need to. Let's see. What if we put height on the y-axis and weight on the x-axis? That actually makes sense. So imagine weight. This would be x over y squared. What would that look like? Z as a function of x, y is equal to that. Enter. Whoa! Look at that! This is our 3D graph that we're looking at. And remember how I told you? This is like, get out. I want to rotate it. So this is generally, this is what this is saying. Your height, your BMI with respect to your height and your weight. So that's what that looks like, which is kind of cool, and it shows how it's a nonlinear function. So you can basically interpret this however which way you like, but I guess it's cool to look at. And I don't know, I work with this all the time, so we're gonna go back to this. So, oh, it's gonna go back to a double of me. Oh my goodness, it's like infinite me's. Oh no! What have I done? Oh no! Oh god, why? It's going on forever. Does this ever clear up? Does this ever end? Let's fix this. Okay. So basically, this 3D graph. Man, I didn't realize that would happen. That's actually really funny. So this 3D graph basically expresses height on the x-axis and weight on the y-axis, and it really shows the relationship and how your BMI basically explodes as your height goes, actually as your weight goes up, but your height generally only increases a little bit. So it's more of a function, it shows how it's more of a function of your weight than it is your height. And you can actually really see that, as in it's squared, but it's being divided by, so that's your height, and your weight is more, so you're basically dividing more of your height out, is basically what that function is saying, which really, it changes, it really explains why that graph looks like the way it does. For example, if you weigh a lot, but you only increase a little bit in height, it just shows, which means your BMI increases a lot more for weight gain than it does, say, for height loss, if that's ever a thing. I know some people lose height, but you know, I'm not judging. It happens. Alright, we're gonna go back to the weird parallax infinite maze until I fix the OBS, so I'm sorry about that. Oh no. Let's get this back on top. Okay. That was scary. So basically, that's what this function is describing. I know I just went into like a 15-minute rant, but worth it. Now I want to see my analytics again. So we have 2 people watching actually, so that's good. So whoever's watching on the stream. Okay. So 33. A 1.8 tall woman has a BMI of 232. What is her height? This is like basic questions to ask. And it's basically like a formula like any other that you can plug in. So you basically say your BMI is 232.2 equals a weight of W over a height of, what, 1.58 meters. So obviously BMI is calculated in metric units because everyone uses the metric but us peons here in the United States, so you know, that's the way we work. So it turns out W is going to be equal to 232 times 1.58 in solving, and I'm just going to leave it at that because, you know, that's a valid numerical answer, and you don't have to simplify, because why would you do that unless you're a chump? So, yeah, let's go to the next question. 35. For a weight W in pounds and height H in inches, well, it turns out you can. Oh, it does an approximation of the formula. So it's a different formula that's more awful when you use imperial. I know I have a bias against Imperial, even though like I use Imperial more often, but it's just because I'm an American. I'm here because I'm an American, right? America, America, America. Yeah, we're not gonna do that right now. 55. So check this approximation by converting the formula BWH. So it basically wants us to convert the formula IR and check that the approximated formula that they give us is the same. So FWH for us American folk is going to be 703 weight over your height squared. So basically, it wants us to check the formula. So in the original formula, height is measured in meters, right? And weight is measured in kilograms. So it wants us to convert from meters into inches, which is kind of crazy. And it wants us to convert from kilograms into pounds, it looks like. So W is in pounds, and our height is in inches. So that's fun. We do know the approximate conversion factor, where 1 meter is about 39 inches, and I believe 5 pounds is about 3 kilograms. So boiled down, 1 pound or 1 kilogram is 3 divided by, it would be 5 divided by 3 is 5/3 pounds. You know, because a pound is bigger than a kilogram. So 1 kilogram is equal to 5/3 pounds. Right. So using these approximate conversion factors, we could actually pretty closely determine if the above number is roughly correct. So let's do that. It's either that or look up the official conversion, and I'm too lazy to do that. So our height is being squared, so let's do that. So 5/3 squared, actually no, 39, no. So for us, we're going from meters into inches, which is smaller, so we're actually multiplying. So we're basically multiplying by 39. So 39 squared is going to be equal to some number. Let's do that out real quick. 9 times 9 is 81, 3 times 9 is 27, 28, cross that, cross that, cross that. 2 times 9 is 27, 2 times 3 is 9, plus 2 is 11. Add it, 8, 8 plus 7 is 15, create a 1, 2, 3, 4, 1458 looks like. So we have that on the bottom, and on the top we have our 1 kilogram. So we're multiplying. Well, we were basically multiplying by 5/3, right? So we basically have 5/3 times. I'm not sure if this is correct or not, but let's double check that. Let's double check the answer to see if I'm doing this correctly, because I feel like I'm not. This is why you check the answers, people. because first you attempt to do the problem first, but if you're lost, you can somehow re-engineer it, and you still end up learning something that way. Trust me, I've done this all. I've done this for a long time. I know what I'm doing. This is the one issue I had. Let's see, question 33. What's question 35? It doesn't have it? What? It just doesn't exist. I don't know if I'm right or wrong. I feel like I'm wrong, so we're just going to move on. We'll come back to that later. 37. A cable company charges $100 for a monthly subscription to its services, and $5 for each special feature movie that a subscriber chooses to watch. Oh god. Who uses cable anymore? I feel like no one uses cable anymore, but that's besides the point. Okay. Write a formula for the monthly revenue R in dollars earned by the cable company as a function of S, the number of monthly subscribers it serves, and M, the total number of special features movies that its subscribers view. So this is actually going to be like a plane within 3 space, because it's a very simple function. We actually call this a linear function. I know most of you refer to linear functions as lines within 2 space, but when you go to 3 space, they're planes. It's pretty much the same, so you're just adding a 3rd dimension, that's all. So for us, this is going to be R as a function of S, which is the number of monthly subscribers, and M, the total number of special features movies. And we have to somehow get those into the revenue. As R in dollars for the monthly revenue is equal to. So here it says 100 for monthly subscription. So and the total number of special features. That its subscribers view. Okay, that's actually a little bit easier. So for us, that's going to be S times 100, right, plus I feel like that's wrong though somehow. And M, the total number of special features. And it says it has $5 for each special feature that a subscriber chooses to watch. Yeah, we'll just put it on as 5M, right. And we have to be really clear between S's and M's because that confuses the heck out of me. I don't like when we use that. Okay, as predicted, this is pretty much a plane, right? You basically have a slope of 100 within the S direction, so that's one axis, and you have a slope of 5 within the M direction, which is the other axis, which makes a plane, or as we know it, a linear function. So that's fun. I'm just going to rewrite this because I made it look a bit odd within the notation. There we go. So that's that. That's fun. That's the nice thing. 39. A heating element is attached to the center point of a metal rod at time t equals 0. Let h equals f dt represent the temperature in degrees C of a point d centimeters from the center after t minutes. Okay, it's a lot to break down, so let's break down the information first. A heating element that we don't care about, it's just an object, is attached to the center point of a metal rod. So we basically have a metal rod here, with the heating element in the center, right? At time t equals 0. Let the function h equals f dt represent the temperature in degrees C of a point d cm from the center after t minutes. So basically what this function is trying to model is the conduction of heat from the center heating element to the periphery of the rod as a function of time. So in terms of our axes, you're going to have time on the x-axis and that's going to be weird. And your place within, in terms of the length of the rod on your y-axis, and your heat overall is the z-axis. And then again, you have a surface. So, that's cool. So, we are basically halfway there with part A. It says A, interpret the statement f of 2, 5 is equal to 24 in terms of temperature. So in this statement, f, so at time t equals 2, which is, and really? They put a point first on the x-axis? Why would you do that? Okay, we're switching axes because the question asked that. Okay, so we're putting temperature on the x. It's really arbitrary the way you do it, so I don't care. But so in this case, f of 2, so basically 2 is equal to, so we're basically 2 centimeters away from the center. Okay, that's fine. And this is at time t equals 5. So at 2 centimeters away from the center, after 5 seconds, the temperature is going to be 24 degrees Celsius. That's how you would interpret that for question A. Question B, if D is held constant, is H an increasing or decreasing function of T? So if D, so this in turn this is a position. So think of it as taking a slice. So we're taking a slice of D as a function of centimeters away from the center point. Has H an increasing or decreasing function of T? So is the temperature increasing with time or is it decreasing with time? Since we're talking about heat that's propagating from the center, where if it's in the center, I guess it depends, because if it's in the center, you get a sudden burst of heat, and then, but you don't take it away, so that means it's going to be increasing with time because that heat actually conducts throughout the rod. So towards the end of the rod, it's going to be colder, and then it's going to get hotter and hotter and hotter as the heat propagates as sort of like this wave that goes through the rod. So that means that the temperature would be increasing with time. So that would be the answer to part B. Part C is if T is held constant, so this is the time, so we're taking the slice of time, don't worry about it, is H an increasing or decreasing function of D? So basically, at say time T equals 0, we'll just fix it there where we have the rod, it's going to be hottest at the center where the heating element is attached, and the heat hasn't even gotten to the end of the rod. It's still cold over here. So we're basically saying the farther away you get from that heating element is the temperature decreasing or increasing. And obviously, intuitive sense says, yes, it's going to be decreasing. So that's the answer to part C. See, I didn't even have to write any of that down. See, I'm saving paper by describing it to you people, so that's going to be fun. All right. Question 41. The monthly payment, $M for a 30-year fixed-rate mortgage, is a function of the total amount borrowed, P dollars, and the annual interest rate, R%. In other words, M equals a function of P and R. A. Interpret the following statement in the context of monthly payment. So this is the same type of question we did before, except we're doing it on 3 different independent variables. Well, 2 different independent variables and 1 dependent variable. So interpret the following statement in the context of monthly payment. So f of 300,000, comma 5 is equal to 1,610.46. So it says, it means they borrowed $300,000, and the annual interest rate is 5%. So the question is, the resultant 1,610.46 is going to be their monthly payment based off of those 2 previous variables. In this case, because they borrowed $300,000 at 5%. And that's the answer to part A. Part B, if P, which remember is the total amount borrowed, is held constant, is M an increasing or decreasing function of R? So basically saying, if you increase the rate, what's going to happen to your monthly payment? Obviously, it's going to increase, which means this is a directly proportional relationship. So that's why we're going to say isn't going to be an increasing function. So when we talk about increasing versus decreasing, when we talk about in 2D, we can think of this as, say, for example, we have, for us, I may have effed this up, but you know what, that's fine. For us, don't mind me, I'm doing this upside down. Basically, if we have our y-axis here and our x-axis here, and we have, for 2D, so we say this is y. That's really odd. Can I write upside down? This is going to be, I didn't know I would be doing this today. Y is equal to x, right? That's our function right there. So basically, let's get this synced up slowly. Let me bring up OBS so I can actually show what I'm doing. Basically, can you even see that? No. Well, you can a little bit. Do we even have light back here? Okay. So you can actually see the line. So this is the equation of y equals x, with the y-axis being here and the x-axis being here. And this shows a directly proportional relationship, because as y is increasing, because as y is going up, x is also going up. So we call this something called directly proportional. And you can see how the function itself is generally going in towards an upward direction. So we call this positive, and we also call this being directly proportional. We also call this increasing. The opposite is true, say, if you have a negative function, where as x is going up in this direction, y is going down in this direction. So the function will look something like that. So, and we call that decreasing. We also call that inversely proportional. We also call that a negative function. But we don't really say positive and negative functions within 3 space, because you can have different angles of plane that. But you can say increasing, decreasing based off of having different things fixed. So that's what we're talking about when we say increasing and decreasing. And so oftentimes for increasing you can also say directly proportional, and for decreasing you can say inversely proportional. I hope that makes sense. So for us, the question is if the total amount borrowed is held constant, is M an increasing or decreasing function of R? So in this case, our monthly payment, is it increasing, directly proportional with our interest rate, or is it inversely proportional with our interest rate? Intuitively, we know that if our interest rate increases, so is our monthly payment. So we know it's directionally proportional, so we know that it's going to be increasing. So that's the answer for part B. Part C, if R is held constant, basically our interest rate, and we're taking a slice of that, is M, our monthly payment, increasing or decreasing as a function of our total total amount borrowed, P. So in our case, does the total amount borrowed is it directly proportional to your monthly payment, or is it inversely proportional? And of course, intuitively, again, we know as the more you borrow, the more your monthly payment is going to be. So we know that's also directly proportional. So we also know it's increasing. So overall, this function, when you without the slice, is gonna look like this bowl that opens up in directions like this, because it's overall directly proportional along both axes. So that's cool. Question 43. So that's the answer to part C. Question 43. A cube is located such that its top four corners have the coordinates -1, -2, 2, -1, 3, 2, 4, -2, 2, and 4, 3, 2. Give the coordinates of the center of the cube. So again, we can actually use the distance formula to determine this, because we actually have 1, 2, 3, 4 coordinates to do that. So we can actually find the average of the first two coordinates and the average of the second two coordinates, and then we can have the average of those resultant coordinates, and we can have the coordinate of the overall center of the cube. So for us, we have -1, -2, -3, and -1, 3, 2. So that's our first set of calculations, and we're basically going to find the average of this. So this is something called the distance formula. So it's basically taking the average of 2 points, and again, it's derived from Pythagorean theorem. And for us, that's going to be x1 plus x2 over 2 plus y1 plus y2 over 2 plus z1. So basically we're averaging the coordinates. So let me get an eraser. Where'd my eraser go? Did I magically just... What happened to it? Oh, it's right there. I am also brilliant at losing things. So we're going to basically find the average in order to find the middle distance. I hope this makes sense. So the average between the x values, -1 and -1, is obviously -1. The average between -2 and 3, we can actually do this. -2 plus 3 is 1 over 2 is equal to 1/2, so 1/2. And -3 and 2 is the same thing, but reverse. So -3 plus 2 is -1 over 2 is equal to -1/2. And that's our averaged coordinate, -1, 1/2, -1/2. Again, we can do this to the other 2 points, which is the other 2 corners. So say we found this corner and this corner, and we found the average. And we're finding, say, this corner and this corner, and we're finding the average. So then we'll have these 2 points, and they'll be connected by a line. And at some point, it'll cross the center of the cube. So when we find the average, it'll be in the middle of these 2 average points. So, as such, we're going to find the average of the next 2 set of points. For us, that's going to be 4, -2, 2, and 4, 3, 2. So the average of 4 and 4 is 4. The average of -2 and 3, we already know, is 1/2. And the average of 2 and 2 is 2. So the 2 points we're averaging are -1, 1/2, -1/2, 4, 1/2, 2. So again, we're going to find the average again, so we can find the overall center of the cube. So -1 plus 4 is 3, and 3 divided by 2 is 3/2. So that's our first coordinate. 1/2 and 1/2, the average obviously is 1/2, so we don't have to do anything with half. -1/2 plus 2 is 2 minus 1/2, which is 3/2, and 3/2 times divided by 2 or times 1/2 is going to be 3/4. So our overall coordinate, that is the center of the cube, is 3/2, 1/2, 3/4. So that's cool. And my loose leaf textbook is taking a beating, and like this page is falling out, but that's fine. So let's actually find the answer and make sure that this is correct. Because that's 43. 3/2, 1/2, and I actually got the third coordinate wrong. It actually should be a -1/2. So somehow I think I may have messed this one up. So 2, 2, that should be 2. Okay. 2 and 2 is 2. -1, -2, 2. Well, that's why I got this wrong. I didn't even write the coordinates down properly. -1, -2, 2. -1, 3, 2. 4, -2, 2. 4, 3, 2. So, why would... So the average of 2 and 2 is 2. The average of 2 and 2 is 2. So that would be 2. Why is it -1/2? That's odd. Well, we can actually try a different way of solving this then. So we can actually draw this cube as best we can. It's on a coordinate system. So, here we go. So on the slice z is equal to 2, we have our y and x, and our coordinates are -1, -2, -1, -2, so that's going to be like right there. And the other one is -1, 3. 1, 2, 3. So those are the two corners right there. And at the slice wait. Oh, it says that its top 4 corners have the coordinates. Okay, so basically it gave us the coordinates on the slice. Z is equal to 2. So this plane that's sitting right here, and the top 4 corners of these. So that's why all the z values are the same. So if we average all the z values, obviously that's not going to make any sense. So we basically have to figure out the length of this cube to figure out, well, how far is halfway down. And for us, it looks like, because it's a cube, we can actually find the distance between 2 of the corners on either of the x or y parts. So in this case, we'll look at the first 2 points with respect to y. So it looks like the difference between 3 and -2 is 1. And again, this is confirmed with 4 minus 2 is 2. That's odd. -2 plus 3 and -2, which is a distance of also 1. And we can actually see that here. -1 and -1 and 4 and 4. So we actually get that we have a distance of 1 here. And -1 and 4 gives us a distance of... Really? That's weird. 3, -1 and 4 gives a distance of 3 between those x values. That's bizarre. Why would it give the... It's the same blimmin' x value, it's the same y values though. So within the sheet z equals 2, you have the same y values of -2. So we have 2 points along y equals -2 here, and y equals 3 here. And it's 1 part away, but here is 3 parts away, so that's not a cube. That's not a cube. I don't think I'm missing anything. This book, I just don't understand where it's getting these questions from, honestly. We could draw the cube. I mean, I don't see why not. Let's do some 3D graphing. Let's get rid of that. No one cares. No one cares. Shut up. Shut up. Leave page. GeoGebra's hosed. GeoGebra, because this is on the sheet z equals 2, we can actually just graph on a 2D graph. Let's do that. Okay. I know Desmos is a little bit faster, so let's do that. Okay. Let's graph this. It's the lengths you go to find the length of a cube. Okay. So it gives us the coordinates. We're ignoring the z coordinates. We're just assuming this is on the sheet. Z equals 2. Negative 1, 1/2, or negative 1, negative 2 is one coordinate. Negative 1, comma, negative 2. It doesn't. It needs to be in order in the parenthesis. So that's that point there. Next point is negative 1, 3. Which makes sense. The next point is 4, negative 2. That point there. And the point 4, 3. I do actually see how that makes a square. Well, in our case, that's the face of a cube. Huh. Weird. I'll make sure to bring my graphing paper. So for us, that looks like it's 1, 2, 3, 4, 5. It has a length of 5, basically. And 3 plus 3. Oh, it's a distance. You add the total distance. So if we have, are we following the cursor? Does it follow my cursor? Okay, please follow my cursor. Okay, it does actually follow my cursor. So if we have here 3 and negative 2, which is a green, we actually have to add this piece with this piece. So 3 plus 2 is the overall distance, which gives us a distance of 5. So we're measuring the absolute value. So that's where I was missing the algebra part. So basically we're taking the absolute value so we can actually find the total distance rather than adding the 2. Because if you add 3 plus negative 2, that gives you a distance of 1, and obviously this right here is not a distance of 1. It's a distance of 5. And you can actually see here along the x values between this one and this one. If you add 1 to 4, that also gives you a total distance of 5. So you're basically taking the absolute value of the coordinate plus the absolute value of that. And actually, that's how you derive the distance formula. I just don't have the distance formula on hand. You don't really need the distance formula if you can figure out conceptually what's happening. So that's why you have to take the absolute value, otherwise you'll get the wrong answer. So now we know that the leg of one, the edge of one cube, one of the edges of the cube is equal to 5, which means all of them are equal to 5, which means going down from 2, we need to get a distance of 5, so we can actually create a number line to do that. This is like the most backwards way to solve a problem, but you know, who cares? I don't. I have a lot of time, and I want to be very thorough in explaining this to you. Boop. Okay. So, we are on z is equal to 2. We want to find out where the bottom is. So we go to 0, so that takes away a distance of 2, and we have 3 left, which means we have to go to z is equal to -3, which means basically we have to find the average of these two. We basically have to find the distance of these two and find the middle or the median. So we'll -3, -2, -1, 0, 1, 2. We find it's -1/2, which is why it's -1/2, and not 2. If we take the average, we can actually see -3 plus 2 gives us -1. Divided by 2 is -1/2, so actually that would have worked as well. -1/2. Boom, we did it. So the only thing you have to be careful of is when it's asking the top of the corners, and also when you're basically trying to find the distance between two rather than the average coordinate. When the average coordinate, you can just average them and you'll find the middle. But if you're actually finding the total distance, that's where absolute value comes in. That's like the distance between speed and velocity, because velocity is a vector. So because of that, it's going in a specific direction. So if you go in this amount of time, but then go back, your total velocity is basically going to show, you know, your speed with respect to distance and time. So it's that total amount of, so it's basically not the total amount of distance you went, but the total amount of displacement you did over that period of time. So that's basically from here to here instead of here to here. Your speed is the total amount of distance over time, and you don't care about displacement. So that's analogous to the situation in which I just described. So that's cool. So that's why it's -1/2 for the answer. What a weird roundabout way to explain that. But, you know, math is fun, so I don't mind doing that. 45. Describe the set of points whose distance from the x-axis equals the distance from the yz plane. What? Okay. Describe a set of points whose distance from the x-axis. So if we imagine, again, 3 space, and the x-axis is here. So the distance from the x-axis coming in this direction, or this direction, is equal to the distance from the yz plane. So if x is here, y is here, and z is here, that means the yz plane is this whole plane going here. And this is the x-axis coming out of the yz plane. So basically the x-axis is perpendicular to the yz plane. So it says it wants to describe the set of points whose distance from the x-axis equals the distance from the yz plane. And it wants that relationship. So I imagine it would be like a plane. So like for us at x equals 1, there would be a distance of 1 away from the x-axis, and you need to have a distance of 1 away from the yz plane. So you would have a point that's also 1 away, so you'd have a point of y equals 1 and z equals 0, so that would basically be the entire line here. Actually not, it would be there. But this would be farther away from the x-axis, so it would have to be farther from the yz plane to compensate. So it would actually look like a plane going this way. So that's the set of points, is this plane going this way. So that's cool. So we call this a directly proportional relationship, I think. It depends on what you're talking to with respect to. With respect to x, yes, it's inversely proportional. But with respect to y, it's directly proportional. That makes sense. In a sort of weird way. Next, 47. Does the line parallel to the y-axis, so that would be this axis here, through the point 214 intersect the plane y equals 5? If so, where? So we're basically saying the point is at y equals 1, and it's parallel to the y-axis. So if the y-axis is here, then let's sync this up a little bit. If y equals 1 is here, 0, then y equals 1 is going to be here, and they run parallel with each other. So it's asking, does this line intersect the plane y equals 5? So the plane y, so this is at y equals 1, because it goes through the point 214. This is the y-axis where y equal to 0. And it's asking if this, so for you folks, so it's turned around because I'm actually opposite. This is like a mirror for me. So for us, this is the y-axis. Actually, this is the y-axis. No, this is the y-axis, and yeah, I was doing this. Never mind that, I'm doing this correctly. So the plane y equals 5 is like way over here. It's like way over here. So at no point is this at y equals 1 going to go to y equals 5. This whole plane over here. So the answer is no. So that answers that question. 49. Find the equations of planes that just touch the sphere x minus 2 squared plus y minus 3 squared plus z minus 3 squared equals 16 and are parallel to A, the xy plane, B, the yz plane, and C, the xz plane. So this is actually a pretty simple question. So we basically need to construct the sphere in 3 space and figure out what that looks like. And then just find spheres that are along the orthogonal axis, planes along the orthogonal axis that are tangential to that sphere. So basically our sphere has a radius of 4 around the point -2, -3. Actually no, 2, 3, 3. 2, 3, 3. Has a point radius 4, so that's cool. And it just wants the equations of the planes. So for the xy plane, that's when x is equal to something. So this is for the xy plane. This is when z is equal to z is fixed. So for us, that would be 2, 3, 3. So radius of 4. So 3 plus 4 is 12. So the question of A would be z equals 12, and that would be tangential to the sphere there. Cool. The xz plane, so y is fixed. So again, radius 4, 2, 3. So 3 plus 4 again. Y would be equal to 12 in that case, and be the yz plane, so x is fixed. So 2 and 2 plus 4 is 6. So you would say x is equal to 6 for that plane. Done. 51. A cube. Oh no, the cubes again. A cube has edges parallel to the axes. One corner is at A is equal to 5, 1, 2. And the corner at the other end, the longest diagonal through A, is b is equal to 12, 7, 4. So, cube has edges parallel to the axes. So that means it's not rotated weirdly, like you could have a cube like that. It means it's sitting nicely. Okay, that's good. One corner is at A equals 5, 1, 2. And the corner at the other end of the longest diagonal through A is B is equal to 12, 7, 4. So it's giving us one corner here and one corner here. Okay, that's fine. What are the coordinates of the 3 other vertices on the bottom face? So what's these coordinates here? And B is what are the coordinates of the other 3 vertices on the top face? Oh, okay. So basically what we're trying to do is find the overall distance between the 2 points. That way we can basically find the height of this, so then we can find the distance between one adjacent vertex and another adjacent vertex, because these two are not adjacent vertices. So, that's cool. So let's actually do that real quick. Let me actually look up the distance formula so I don't do this like a chump, because we already explained the derivation of the distance formula. Distance formula 3D. Distance is equal to let's get it from my math textbook instead of from interwebs. Distance in our case is going to be the square root of x2 minus x1 squared plus y2 minus y1 squared. And then we just tack on plus z2 minus z1 squared. Cool! Now we can basically find the distance of these two functions empirically rather than graphically. So our first point, A is equal to 5, 1, 2, and B is equal to 12, 7, 4. So we're going to put this into our distance formula. So we'll say B is our 2 point, and A is our 1 point. So when we do that, it's basically 12 minus 5 squared plus 7 minus 1 squared plus 4 minus 2 squared. And then we can do this out operationally. 12 minus 5 is of course 7. 7 minus 1 is of course 6. Oh, but that gives us the distance. We want the midpoint formula, don't we? That's why I've been doing it differently. Yeah, we're just basically finding the average. Never mind. Ignore what I just said. The midpoint formula is basically finding the average of the two. So we're actually going to do the same thing. Because why not? 5, 1, 2, and 12, 7, 4. The average between 5 and 12 is 5 plus 12 over 2. It's equal to 2 plus 5, 7. So 17 halves. Okay, that's cool. So that's our first coordinate. $17 halves is our x value for that coordinate, for the midpoint of the center of the cube. The distance between the average value of 1 and 7 is 8 over 2, which we of course know is 4 for our y value. And the average between 2 and 4 is 4 plus 2 is 6, divided by 2 is 3. So our overall midpoint, and in this case is the center of the cube, is 17 halves, 4, 3. So that's cool. So we can actually see how far up Z we are. And so it turns out that the distance between one vertex and another is 6. So 6 is our magic number. Okay, that's cool. So now we can find the vertices of all the faces. So it says A. So A, let's let A be the A be the top face, and let B be the bottom face, on the bottom face. So it was an element of. That's what this E thing looks like. It means it's an element of. It means it resides in. You'll often see it in linear algebra, occasionally in Calc 3, but most often I'd say in group theory. So that's cool. So A is an element of the top face, B is an element of the bottom face. So we can actually say this because I think that's true. 5, 1, 2, 12, 7, 4. Actually the reverse. So the reverse has to be true because empirically, because 4 is greater than 2, and 4 is on B, and 2 is on A. So B is actually on the top face, and A is on the bottom face. So now that we've got that sorted out, we can basically just add 6 to the various axial orthogonal axes with respect to the orthogonal axes, so we can find the 3 other vertices within that square that makes up either the top face or the bottom face. So we'll start with the bottom face with A. So that's 5, 1, 2. So we're not adding anything to our Z. We have to remember that. So if we add 6 to 5, so we get 5, 1, 2 is one coordinate. If we add 6 to 5, our x-axis which is with respect to the x-axis. So 5 plus 6, that's going to give us 11, 1, 2. And if we add 6 to 1, that's going to give us 7. So 5, 7, 2. Then we need the last point. So you actually do it to one of the resultant points that we got before. So you start here, and then you go here or here. But we need to get back around, and you can't just add. So you have to basically add 6 in one direction and then add 6 in the other direction. So we know we added 6 to the x to get the point 11, 1, 2. So now we'll add 6 to y. So in this case, we'll have 11, 7, 2. That's all the 4 vertices that make up the bottom face. And then we'll do the same thing to the top face. So the top face is the point 12, 7, 4. And we know the magical number is 6. So 6 plus 12 is actually really the same as 3 times 6, which is 18, 7, 4. And we'll add it to the y. So 6 plus 7 is 13. So we have 12, 13, 4. And we have to go once in the x direction and once in the y direction. So we'll actually use the So we'll use the point 18, 7, 4. So we've gone in the x direction already, so we need to go in the y direction. So 18, 7 plus 6 is 13, 4. And those are all our 4 points on the top face. And those are actually the 1, 2, 3, 4, 5, 6, 7, 8 vertices of the cube. Cool. And that's that. We could do 53. Oh, it's just find the midpoint, find the point 1/4 along the way. Strengthen your understanding. And it's just more of that. Cool. Let's take a break from that. I'm going to go and grab probably some water. My throat is so dry. It never gets this dry. Probably because I've been talking. Thanks for watching. How long has it been? An hour? It's just been an hour on one section. Explaining it. It hasn't felt like an hour, I don't think. Weird. Like my dead skin. That's weird. That was fun. We didn't do actually much calculus. This was all algebra, but I had fun. I hope you guys had fun. Actually, I might do this again because, it was fun overall, but I need to stop or else I'm going to destroy my voice because I've been talking for so long. That's the thing about videos, you can just edit out the parts, and because you don't talk as much, you don't have to lose your voice. But I've actually been talking basically non-stop for the last hour, so I hope you enjoyed, and we'll see you all next time if you like this. I don't know. So I don't know how to end these videos because this is new to the channel. And this is the only reason that it's here, because this is the only channel on which I have streaming set up. I was going to do it on the vlogging channel, but the streaming isn't set up there. So, get out. Bye. Like leave. Like scram. Go find something else to do. Just stop.